we'll see that actually, like, while we're talking about number theory, we're going to be doing example proofs. So there will definitely be more examples of that. And obviously, we're just going to scratch the surface. Like, you can take a whole course on number theory. I don't think we typically offer a course on number theory. We have in the past, occasionally, but it's a very deep subject. But we're going to cover some of the most basic kind of useful things. What really, this is a study. Basically, think of it as study of the sets, n, and like the natural numbers and the integers. And you might think, I mean, how complicated can that get? Like, natural numbers are pretty simple, 0, 1, 2, 3, what could there be to say about it? Well, if all you care about is addition, then yes, the natural numbers are extremely simple. There's not much to say. But when you throw multiplication into the mix, it turns out that that gets extremely interesting very fast. And there's lots of things that we still don't understand about the structure of, how addition and multiplication interact and the structure of the natural numbers. So, and maybe you don't believe me now, but hopefully after we talk about this for a little while, maybe you'll get a better sense. Why study this? I mean, for a long time people studied it just because it was interesting, and it's kind of like, what could be more natural than asking questions about numbers and primes and divisibility and things like that. Of course, in modern times, it turns out that all this number theory that people were exploring just because they thought it was cool turns out to be the basis for a lot of modern cryptography. So every time that you send your credit card information securely to Amazon or whatever, it's using number theory, like a practical application of number theory to do that in a secure way so that people can't find out your credit card. And I'm not sure we're going to take the time. It would probably take about 3 weeks to build up all the stuff to get to the point where we can actually understand how some encryption algorithms work. I'm not sure that we have time to do that, but we'll definitely learn a lot of the pieces, and I could point you to some resources if you want to then take the pieces that we learned and then go learn how actual encryption stuff works. You will have the tools to do that. And you'll see as we go, there's lots of other things. So encryption is not the only way this is relevant to computing, but that's kind of one of the kind of flagship things. All right. So, but this is really, this is something that people have been studying for literally thousands of years, and so let's jump in. All right. So the first thing that we want to think about is the idea of divisibility. Like, when is one thing a multiple of another thing? And this is something that you all have probably thought about since, I don't know, 3rd grade or whatever, right? Counting by twos or whatever. So, but this is divisibility. Okay, so it's one of those things where probably you have an intuitive idea of what it means, but we're going to write down a formal definition, and we'll convince ourselves that it corresponds to our intuitive idea, but then we can use the formal definition in ways where maybe our intuition might fail us, right? So here's the definition. If A and B are integers, we say that A divides B if and only if there exists an integer k, k ln of z, such that k times a equals b. Okay, folks, hopefully this corresponds to your intuition, right? B is divisible by A means, well, I can, A times something gives me B, right? 8 is divisible by 2 because 2 times 4 is 8. 27 is divisible by 9 because 9 times 3 is 27, right? And we've seen, when we talked about, we made a definition of what it meant for something to be even before. And this is the same kind of thing we just said specifically, if k times 2 times k is b, that means it's even. But even really just means divisible by 2. So they're the same thing. This is just more general. And people use different words for this. So when A divides B, this isn't part of the definition anymore. It's just a remark. We also say A is a divisor or a factor of B. You've probably heard those words before. Or we'd also say that B is a multiple of A. Okay, so those all mean the same thing. And we use the notation and we'll also write this as an abbreviation for not. Okay, so remember the other day when I said, the notation we have for and or and union and intersection, it's very elegant and it fits, and this is like the only time it's ever going to happen. So this is an example of a terrible notation, but it's very standard. So I'm teaching it to you because you probably will see it other places. Why is it terrible? A couple reasons. Number one, vertical lines are used for lots of other things already, right? Like absolute value. Also in set comprehension notation where you have x such that blah blah blah. So imagine if you write x such that x is divides whatever. You've got multiple vertical lines going on. That's confusing. Number two, this is a sort of more subtle reason. This symbol is symmetric, but we'll see that it's not commutative. If A divides B, that doesn't mean that B divides A. And so usually when you have an operation that you can't flip around either way, you want a symbol that doesn't look symmetric because it makes it look like it doesn't matter. Plus is symmetric, and that makes sense because plus doesn't matter which order you do it in, the symbol for plus. But implies is not symmetric, and we indeed have a symbol that it doesn't, if you flip it around, it looks different, right? So it has a direction to it. This ought to have a direction, but it doesn't. Anyway. Oh well. This is a notation that you can use. But if you just read it as A divides B, then you know which way it goes. So I'll just it's terrible. And in fact, this is one of the rare exceptions where this notation, you cannot use this notation in Disco. Because kind of what I said, the first reason, where the vertical line is already used for a bunch of other things. And actually, it would be really, really difficult to get Disco to accept this and to be able to tell the difference between when you're using absolute value and when you're using divides and other things. So it's just too difficult to get it to work. So in Disco, you just write the word divide. I'll show you an example in a minute. So we can also illustrate it. So it's something like maybe it's so here's B. B is like a number that I'm thinking of as a certain length. And then A fits into it, an exact number of times. So I can have, there's some number of copies of A that fit exactly into B. Right? That's what it means that A divides B. Okay, but if I have, so this is A divides B. Here's when A does not divide B. What does that look like? Well, it might look something like this. So here's my B, and you know what I can do is right, so there's some like there's a different color, black, orange. Some like leftover part, which I'm going to call R. So I can fit a certain number of copies of A into B, but I have a little bit left over, right? So, and that usually we'll call R for remainder, right? I draw these pictures just because often when we're thinking about divisibility, thinking in terms of pictures like this can be helpful intuition. Now the pictures don't tell you everything because, like, the definition says, that it could be any integer. So integers could be 0 or negative, and the picture doesn't really show, like, how could you have a negative number of A's or something like that. That works in the definition. It doesn't really work with the pictures. But the pictures still give us a helpful intuition. Garrett, were you?
I was going to ask, how would you, is there a way you show visually why divide by 0?
Yeah, no. I mean, well, yes and no. I mean, maybe you could think about like a picture where you use like, like a 0 length or whatever. But again, the point is the pictures can break down. Like we can't figure out everything from the pictures, but if in doubt, we'll go back to the definitions. But the pictures can be helpful. Pictures can be helpful for thinking about like why we think something might be true in general, and then we can go to the definition of actually true. Okay. So I want to do some examples, and in order to do the examples, I'm just going to show you how to do this in Disco, and we'll use Disco to evaluate the examples for us. But I'm going to try to figure out. Okay, so. You just write it divides. Right, so divides, for example, you can give it two natural numbers and it'll tell you true or false. So, for example, I can say like, 3 divides 6, so will this be true or false? True, right? And remember, well, what's the definition? The definition is, does there exist an integer, k, such that 3 times k equals 6? Yes, you can pick k to be 2. That shows that 3 does divide 6, so true, all right? How about 5 divides 16? True or false? False, right? Okay. Next example, how about 5 divides negative 15? True? Why true? Yeah, right. So the definition says, does there exist an integer that includes negatives, such that 5 times that integer is negative 15? Yes, negative 3, right? 5 times negative 3 would be negative 15. So again, a picture would break down here. I guess maybe you could like draw it going backwards or something, and then you can like, I don't know. It maybe doesn't help to think about a picture anymore, but we can apply the definition, and yes, this should be true. Also, just like intuitively, if we're counting by 5s, we can count up by 5s, we can count down by 5s. We can count 5, 10, 15, 20. We can also count negative 5, negative 10, negative 15, and all those things are divisible by 5. Okay? How about, does important point here, so you're right. 4 divides 8 is true, but 8 divides 4 is false. Alright, so this shows that the divide is not symmetric. You can't, the order matters. That's why I was complaining that the symbol is symmetric there. In fact, like if I have, A divides B and B divides A, is there any situation where that they can both be true? Where A divides B and B divides A could both be true?
Is A equals B?
If A equals B, indeed, yeah, then they would both be true. Is there any other situation where they could both be true? Adam?
I guess if you substitute like n for like the symbol for a real number.
You substituted.
Uh,
Oh, instead of talking about natural numbers, I talked about like real numbers?
Yeah, or we just discussed,
Yeah, no, the definition is just about integers.
Okay.
Yeah. Divisibility doesn't really make much sense when you're talking about real numbers, because like, well, I can always find a real number that I can multiply something by to get anything I want, so. Is there any other situation where both A divides B and B divides A are true, but they're not equal to each other?
If they're absolute values equal to each other.
Yeah, okay, right, so if I'm like, they're negatives of each other, like 3 divides negative 3, yeah. Turns out that's the only two, like if you have A divides B and B divides A, they have to be equal or maybe negative of each other. Kind of an aside. All right, how about, does 0 divide 3? No, why not? And don't say, because you can't divide by 0. What's the definition? Matthew?
Because there doesn't exist an integer where 0 times that integer.
Right, right. Yeah, there's no integer I can multiply by 0 to get 3. So this isn't an error though, right? So I can't write like, oops. So it is an error if I try to do like 3 divided by 0, right? That's actually an error. But I'm allowed to ask, does 0 divide 3? The answer is false. It doesn't, right? It's not an error, it's just not true. Okay. Does 3 divide 0? Yeah, because I can pick 0, right? 3 times 0 is 0. Does 0 divide 0? Seems to not. Why? Olivia? Yeah. It just says, the definition says, can I pick an integer such that 0 times that integer is 0? Yeah, sure, I pick 73. Yeah, 0 times anything is 0. So, this is true. That might seem weird, but, I mean, that's according to the definition. That's true. Okay. Oh, wait. Alrighty. Alright, let's, oh no, I don't want orange. Theorem. And we're going to prove, like, one part of this. So we're going to state a theorem that has a bunch of different properties of divisibility, and we're going to prove, I think, one of them, and maybe you'll do the other ones on homework, or maybe we'll do the rest of them some other time. I don't know. I don't remember how it is, but so let A, B, and C be integers. Then there's a bunch of different things. They're all true. So 1, if A divides B and A divides C, then A divides B plus C. This one except notice that, that makes intuitive sense to us maybe for things like 3, but this really says it's true for any integer, so that would include 0. But we saw just before that actually this is true for 0 as well. So that wouldn't be too hard to prove, but worth stating. That is certainly an important property of the divisibility thing. So if A divides B, then A divides B times C. And 4, if A divides B and B divides C, then what do you think I'm going to write here? What do you think we can conclude if A divides B and B divides C? A divides C, right? So, right now, what I want to do, we're going to write a careful proof of part 1. And the other parts have very similar types of proofs. And I will probably ask you to do at least one of the other parts on a module, but you can be able to use this as an example of how to set up that proof. So first, though, let's draw a picture. The picture will not be a proof, but it'll maybe help give us an idea of why we think this is true. So here's the situation. I have 3 numbers A, B, and C, and I know that A divides B, and also A divides C. So, here's my B, and here's maybe I've got, maybe 2 copies of A fit in B, okay? And then here's my C, and maybe 3 copies of A fit exactly into C. Well, if it looks like this, then when I do B plus C, right, that really just looks like, I get one big line, which is the length of this plus the length of this. Here's B plus C. And I can see that if 2 A's fit in B and 3 A's fit in C, then when I put them together, I'm going to, 5 A's are going to fit in there some, right? So. Does that make sense? Should have started my drawing for really good. Okay, but let's do a proof. So proof. So this is a proof about, or the theorem really is about, it's a for all A, B, and C. So we'll just say, let A, B, and C be integers. I could say let them be arbitrary integers. That's really what this means. When I just say let them be in integers. Okay, and right, we're proving an if-then. We're proving that if A divides B and A divides C, then A divides B plus C. So we'll just say, okay, and suppose divides B, and A divides C. So that's what we're given. And maybe let's like expand out the definitions of these things a little bit. Right? What does it mean that A divides B and A divides C? We can say that is, well, the definition says, right, A divides B means there exists an integer, we'll call it J perhaps, such that A times J is B, and similarly for the other one. That is, there exist integers J and K such that A times J equals B, and A times K equals C. And if I want, I could say, you know, they could say here, like, by definition of divisibility, I wouldn't have to say that, but if I wanted to be a little more clear why I get to say this, right? The reason I get to say this is because I'm just expanding the definition of what does it mean that A divides B and A divides C. Okay, so what do we have to do now? Well, we want to prove that A divides B plus C. And how do we do that? We have to show that there's some integer that we can multiply by A to get B plus C. Okay, but we can do that by saying then B plus C equals, well, I can substitute these things here. So that's AJ plus AK. I can factor out the A times J plus K. Right, thus, let's see, we have shown that B plus C is A times some integer, right? Because of course, since J and K are both integers, when I add them, I get another different integer. Hence, by definition, A divides B plus C. Any questions about that proof? These other ones are all going to be pretty similar, right? You're given some fact or facts involving divisibility, and you can kind of say, well, what that means is there must exist certain integers, blah, blah, blah. And then you kind of try to use some algebra to, you know, get the thing that you're trying to conclude in the form of something times an integer, and then I'll just say parts 2 to 4 are proved similarly. This is not part of the proof. This is just me telling you that they can be proved similarly. But you are allowed, if on a homework, if there's like, you're doing a proof, and there's like two parts that are pretty much identical, except for like one thing is going to be different, you would be allowed in that case to say, you know, the other case is proved in exactly the same way, except that, you know, x equals 4 instead of x equals 3 or something. These would not be similar enough that if I told you to like prove all those things, you wouldn't just be like, oh, the other parts are similar. I would not accept that, but I have to use something to do so. All right. I just want to make a kind of a remark, an aside, and this is going to come back. If this doesn't makes sense to you right now, that's okay. We'll keep coming back to it perhaps. But it's an interesting fact. So by definition, right, A divides B is defined as, if and only if there exists A, integer K, such that K times A equals B. That's just, I haven't said anything new yet, that's just how we define divisibility, right? But also, A is less than or equal to B, only if there exists K, a natural number, such that K plus A equals B. So let's think about this for a second. So I'm saying, if there exists, I've got some A and B. If there exists a natural number that I can add to A to get B, right? So I start at A and I add some natural number, possibly 0, possibly bigger, right? But I add something and I get to B. That means that A is less than or equal to B. And if you look at these, they look very, very similar. The only difference is, well, this has integers and this has natural numbers. But if we wanted, we could say, forget about integers. Let's just think about natural numbers. And just say, if I had a version of divisibility that didn't talk about natural numbers at all, it would still be interesting. Then it would be exactly the same. It's just that, like, divisibility is where we use multiplication here, and less than or equal to is where we use plus here. So, divisibility is to multiplication as less than or equal to is to addition. This is sort of a deep fact, and I don't expect you to like internalize this yet. I'm just mentioning it because it's interesting, and we'll come back to this later. But it turns out that like divisibility actually has a lot of the same properties that less than or equal to has. It's just a different way of thinking of an order on, like an order to put numbers in. All right. So, I'm going to talk about one more thing today, which is called the division algorithm. I don't know why it's called that, because it's not an algorithm. But that's what everyone calls it. Not. It's a theorem, not an algorithm. Anyway. So this is, we're going back to, we talked about divisibility. Let's think about this scenario here. This scenario here where B is not divisible by A. Right? We could still say, well, okay, I can't put a specific number of A's exactly into B. But I can say perhaps like how many A's, what's like the most number of A's I could fit, and then I have something left over. And this is something that you all have been doing since elementary school. When you do like B divided by A, and you write down, oh, the answer is 3, remainder 1, or something like that, right? And so we're going to make this a little more precise. Like what can possibly happen here. So theorem, let A be an integer, and I'm going to say D instead of B, D for divisor. And we're going to say it's a positive integer. We definitely don't want to allow 0, because we don't want to divide by zeros. I suppose we could allow negative integers, but it's not going to really add anything interesting. We can always just, like negate A and D both. So we might as well just talk about positive ones. Here's what it says. Then there exist unique integers q and r such that 0 is less than or equal to r is less than d, and a equals d times q plus r. Right, so here's my, here's my a, here's my d, here's my r, and here's my root. Here's an illustration of this. Right, so A is kind of the number I'm starting with, D is what I'm dividing by. And in this example that I've drawn here, right, Q is the quotient. This is how many times does D fit into A, basically. And then I've got something left over, and that's R. But this says moreover, there's unique values that make this work in such a way that, first of all, R, it could be 0. If A is exactly divisible by D, then I won't have anything left over, right? Then my R would be 0. Or it could be all the way up to, but it has to be less than D. If R is D, or bigger than D, then that means I should have put another copy of A in. Another copy of D. Like if I had a whole bunch left over here that was bigger than D, then I should have put another copy of D in the first place, right? So that's why we're saying R is always going to be from 0 up to, but not including D. Okay. And again, maybe that's familiar to you from, when you're doing division in elementary school, when you did, something divided by 8. If at the end you got the answer is 24, remainder 10. Like, you can't have remainder 10 if you're dividing by 8. That doesn't make sense. Like, you should have gotten one more as your answer, and then had remainder 2. Right, and then this is just saying what we just said, right? A, the number we're starting with, is equal to q copies of D plus the remainder. And if we didn't have this, right, then there's lots of ways to do it. It's not unique. Because I could say, oh, it's like 3 copies of D, plus this whole remainder, or 4 copies plus this, or just 1 copy of D plus this whole thing is the remainder. But when we say, no, R has to be in this range, that means there's only one way to do it. So again, stuff you've probably seen before, but we're giving it a precise definition. We cannot prove this yet because it needs something called induction that we haven't talked about. We may come back and prove this later in the semester once we've talked about induction, like as an example. But proof needs induction, which we'll do later. Okay, so Q is called the quotient. And R the remainder. We also write that Q, the quotient, is a div D, and R is a mod D. Okay, and so this div thing, right? This is what's sometimes called integer division. So it's the thing in Disco I showed you that it was a double slash, right? That does division, but like it rounds down, right? So you could think of it as rounding down, or you could just think of it as telling me how many exact copies can fit, and then forget about the leftover part. And then mod, a mod d says if you divide by d, what's the remainder? How much is left over? Right. And this is, so most programming languages have both of these things. So, like in Python, div is //. In Java, it's just slash, and it depends on whether you use it on integers or on doubles, whether you get like the quotient or whether you get, a floating point thing. Many languages, mod is like the percent sign. So in programming languages, this is like // or slash, and this is percent, or sometimes you have to just write it out as mod. I think, yeah. And these, and I don't think we've seen mod in Disco, but it of course has them. So if you can use percent or you can use the word mod, either one works. Yeah. So let's do a couple of examples. What is the quotient and remainder when 101 is divided by 11? So basically we're asking, like, what's 101 div 11? And what's 101 mod 11? So, well, let's see. 10 times 11 would be 110. That's too big. Right? 9 times 11 is 99. And so that looks like 9 copies of 11 will fit without going over, right? And then our remainder will be 2, right? So we think this is going to be 9 and 2, right? And just to check, like, does this fit the definition, like that theorem? Yes, because 11 times 9 plus 2 is 101, and, right, 2 fits the definition of where it's supposed to be. It's in between 0 and the divisor. Let's do, for example, what's 55? Somebody will think, if I do 55 divided by 11, what do I get as the quotient and remainder? Five and zero. Yeah. So right, if it's exactly divisible by the thing, then you're definitely going to get remainder 0. Okay, and then how about, what if I do 7 mod 11? So when I teach 150, we talk about mod. This is usually confusing for students. But we can apply the definition. That'll help us think about what this is. So, the other thing, if I take 7 and I divide by 11, what's the remainder? Adam? 7. 7. Why 7?
Well, I'm thinking it doesn't go into, well, 11 doesn't go into 7, like, even one full time, so it would be 0.
Right.
I mean, not technically, but it goes into it
Yep.
0, 0 times.
Yep.
And then there would be 7, the remainder of 7 left over from that.
that?
Wouldn't it be a remainder of 11, not 7?
Well, the remainder definitely has to be less than 11, because remember, the remainder is always going to be from 0 up to less than the numerator, right? No, I think Adam's right. So this is 7. And we could also say that 7 is 11 and 0, right? And by definition, we're looking for, you know, if I know that I want q times 11 plus r to be equal to 7, you know, whatever q and r are, well, the only way to make that work is if I make q 0 and r 7. Well, and r has to be between 0 and 11, right? So, okay, here's one more, we have time for one more example, which is slightly misleading. What is negative 24 div 11 and negative 24 on 11? And you can try these all out and just go if you like. But negative 2 and negative 2, so now he says, look, 11 times negative 2 would give us negative 22, with the remainder of negative 2. What do you all think? Sounds right? Not right. There's nothing wrong with his math, but yeah, I don't know.
It's negative 2 and positive 2, say, for dividing by 11, negative 2 for mod, is greater than
No, but no, if I do, like, negative 2 times 11 is negative 22, and if I add positive 2 to that, I get negative 20. That doesn't mean the right thing.
Yeah, I just thought it was pretty, but yeah.
Well, it's not really a trick question. The reason it's not right is that the remainder is supposed to be between 0 and the divisor. That's not. So we're out of time, but I'll let you think about how to fix it. The element.